what we're going to be going over here is just a basic problem here where we'd be using linear programming or linear optimization, where we'd be actually applying some linear algebra to maximize some, in this case we're going to be maximizing some profit here on two different products we're manufacturing. Okay, so when we're talking about maximizing profit here, we have to set up an objective function. And really when you're looking at accounting or cost accounting here, when you're talking about profit here, you really have to base it on contribution margins. So in this case, we're going to have two different products here, product S and product B. So we have to determine the contribution margins on each. So we're going to have a selling price here on product S of $800 and a variable cost, all our variable cost, direct labor, material, and overhead and so forth here is $560. So that difference here gives us a contribution margin of $240 for every unit of product S we sell. And then for product B, selling price of $1,000 and its variable cost here is $625. So that difference gives us a contribution margin of $375 for each product B we sell here. Okay, so this becomes our profit or our objective function here in linear optimization here. So profit here equals $240 for each S, or 240 times S here, plus $375 times B here. So that becomes our objective function here. This is what we have to optimize. Okay, so the next thing we have to deal with is capacities here. And this is what these two products are competing against here, some different capacities. So let's look at it in these terms here. We're going to have the two products here, product S and product B, are going to be going through the assembly test, and there's also going to be some material capacity here for product B here. So first thing you have to do is you have to determine your available capacity, and we'll do it in terms of hours here. So for our assembly operation here, we only have 600 hours available to produce both product S here and product B. And testing, we have 120 available capacity hours here for testing, and that has to be divided between product S and product B. So the next thing we have to do is we have to set up the use of the capacity here. So we're going to determine that for product S here and product B here. And then we'll also look at the maximum units we can produce here. Okay, so for product S, we're sitting with assembly here. It's going to take 2 hours here per product S here. So available capacity 600, 2 hours per S here is going to give us a maximum units that we can produce here for product S is 300 units. That's assuming we don't produce any product B. And then for product B here, it takes 5 hours per unit for assembly, 600 hours, divide 5 into that, and we're going to get maximum units for product B of 120 hours. That's assuming we don't produce any of product S. And then same thing for our testing operation. Product S takes 1 hour, and divide that into available capacity, 120 hours, you're coming up with maximum units for product S here, 120 units. And then for product B, it takes a half an hour here of test time. Available units 120, divide that out, and you're going to get product B. Maximum units you can produce is 240, assuming you don't produce any of product S. And then we have one other restriction here, and we have a material restriction here for product B. We only can acquire enough material to build 110 units here of product B. Okay, so this is what you're going to have to do when you're talking about this linear programming or linear optimization, when you're dealing with these different operations and different products that have to be allocated to those different operations here based on available capacity. Okay, so the next thing we have to set up are linear equations here, and we're going to have to set up our constraints based on our available capacities and how we assign them. So for the first thing we have to do here, let's look at the constraints we're going to dealing with again as the assembly, the test, and that material constraint. Okay, so setting up our linear equations as they are here. So we're going to work off our capacity table here. So for our assembly, our constraint is what S here. We got 2 hours for every S here, plus 5 hours here for every B. 2S plus 5B has to be less than or equal to the total available capacity for assembly is 600 hours. Okay, so that's for assembly. For test, the same thing here. 1 hour for product S here, so 1S plus a half an hour here for per product B. So 5/10 times, or half an hour, or 0.5 here times B. 1s plus 0.5 B here, or 5/10 times B, has to be less than or equal to total available capacity here for testing, 120 hours. Okay, and then finally we have one other constraint, and that's that material constraint here. For the maximum units that we can produce here for product B is 110. So for product B here has to be less than or equal to 110. And then we can't have any negative production here, so we'd have to say that S has to be greater than 0, equal to or greater than 0, and B has to be greater than or equal to 0. Okay, so those are our constraints coming off our capacity table. So the next thing, we just have to set up our graph. What we're going to be looking at here is just a simple graph here, and two-dimensional graph here, to determine our maximum profit between these two different products here. So for assembly, you can solve for either one here. You can either solve your equation here for B or for S. So let's just look at it in terms of S. So S here, after solving, let's look at our first equation here. So S, you move S here. Well, first off, just take and move your 5B over to this side of the equation. You get 600 minus 5B, and then you get 2S. Just divide total amount here by 2. So for S, for every S here, assembly time, it's going to equal 600 minus 5B, that difference divided by 2. And for testing, same thing here. Solving for S, you get 120 here hours minus, just move your 0.5B over this side of the equation. Okay, so that's for S here for assembly and testing. And then for the material here, we'll just say B is equal to 110. All right, this less than or equal to, for our graphing lines, we just put all equals here. That's the only thing. No big thing. The only thing is you have to solve for either B or S here to determine those line functions. And then here S, again, S has got to be equal to 0, or B is equal to 0 here. All right, so those are setting up our constraints here based on our capacity limitations that we have here between those two different products. Okay, so that's the key here when you're dealing with linear algebra, linear optimization, or linear program. You have to come up with these basic equations. Okay, so now let's go and let's graph this based on the constraints and the graphing lines that we have here. Okay, so this is it. We're going to lay it out on 2D, and we're going to be looking at line intersects, or we have to determine the bounds here, what they would call the bounds for this these two different products based on our constraints. So what I've done here, I'm just taking our product S here in units. That would be in our x-axis along here, and then our y-axis here represents the product B in the number of units that we produced here. Okay, so of course we start out with 0, 0. We got those three different lines. That's what we have to come up with. We got those three different lines here that we have to lay out on our two-dimensional graph here to determine the bounds. We got to find some region in, or some maximum profit here based on those constraints here that we have. Okay, so for just looking at this green horizontal line here, and that represents B, our material constraint here, at 110. So we just, from B 110 for just constant right across here, regardless of how many units we produce a product S, it's constant. A constraint here, we can only produce 110 units of B here. Okay, so then our other two constraints is, let's just look at this blue line here, this this downward sloping blue line here. So that is really our equation we have here. S equals 120 minus 5/10 B. So for S, for when B is just setting B equal to 0 here, when B equals 0, S is going to equal 120. All right, and then if you set S equal to 0, then you just solve for B. So B is going to equal what? 240 here. Okay, if you plug those numbers into your equation. So you got your blue line here based on your test. That's your constraint here on your testing. And then this red downward sloping line here, that's for our assembly. And that was, again, we looked at in terms of S equals 600 minus 5B here divided by quantity of 2. So again, if we just determining your X, or your where your intercepts here on your axis is, and that's what we did here, this one here, we're determining our intercepts. We're always trying to determine our intercepts here on our axis. Okay, so for S here, what are we sitting with? When B is equal to 0 here, 0 units, what is S? Just B equals 0. S is equal to 600 divided by 2. That's going to give us 300 here. So S equals 300 here when B equals 0. And then is solving when S is equal to 0, B is equal to what? I don't know. Whatever it figures, it's going to figure out to some number up over here. Whatever that is here. But it's not sitting in our bounds. It's not a line in our bounds. But that's how you have to lay out this line here. When we had what? Let's put it in here. When S equals 0, B is going to equal whatever it figures out here. You have to solve here for the B, and you're going to come up with some quantity here. Okay, but nonetheless, that's laying out our line here. Okay, so now for our different points here. We know this point here. That's where S is 120 here when B equals 0. So our XY coordinates, S is our X coordinate, Y here is our B coordinate. So that would be, at this point, it's 120 and 0 here for S 120, B equals 0. And then going up here, and we're looking for these points here. We're trying to lay out those bounds, and we're looking for the maximum profit that we're going to have here on these lines. And our maximum profit's going to lie on these corner points here. So what we're going to look at is our profit's going to be in this region here based on the bounds or those restrictions or those constraints we have here. So this one here, this point here where S equals 0, then B is equal to 110. So you got 0, 110 coordinate there. And then you have that intersection here between the green line here and the red line. And if you plug those numbers in, you're going to come up with S at 25 units, B at 110 here. So you got those 2 points, and then you got this last point here. And that's just setting those 2 different equations equal to 0 here. Well, you have to find out what B and S is here. So you know that S, you just set this 120 minus 5/10 B is equal to 600 minus 5 of 5B divided by 2. And you're going to solve for B, and you're going to come up with B sitting at what? 90 units here. And S, when you plug it back in here, you solve for B at 90 units, go back to either one of your equations and put in S, and you're going to come up with 75 here. So those are the 4 points that we have to deal with here. Actually, you have to deal with these points here on the line as well. But you may have some different your profit is going to fall either on those lines or at the bounds that we're talking about here. And really, it's going to fall at the corner points here. So we've done that. Now let's just go and we're going to find out that our maximum profit is going to be at this point here, 75 S, 90 B here. Okay, so let's just go and let's just plug it into our equation here. So our profit here equals 240 S plus $375. Those are dollars here plus B. Add those 2 quantities. So just looking at this first point here, where S equals 0, B 110, you're going to come up with, plugging them in here, you're going to come up $26,400. And then at this other, that was that, what, that 110, where was that point here? That was that point right here, just to correspond it. And then you got that next point here, 25 S, 110 B. That's this point here. You plug those coordinates into your profit function, you're going to come up with $47,250. Okay, so that's for that point. And then this other point here, this is where we're going to come up with our max profit here. And let's look at that. So that is what? It's 75 and 90. Okay, you come up with that 75S, 90B. Put it into your equation, S, and your profit equation here, and you're going to come up with $51,750. And then this last point here where we're making just all units of S, 120 units S, 120 S, 0B, it's this point right here, you're going to come up with what? 20, plug it into your equation here, profit equation, your objective equation here, come up with $28,800. Okay, so we determine our maximum profit just by laying out, first off, graphing these lines here in 2Ds with those constraint lines. With 3 constraints here. We had to solve for the corner points here based on doing some simple algebra and understanding how we'd apply our simple algebra here to determine our constraint lines here. Okay, so that's just going through the graphical approach here to determine the maximum profit here. All right, so let's just go look at it in these terms here. Now, this graph here, I got it switched. The axis is, I got B units across our x-axis, S units across our y-axis here. Just reverse them so you can't really relate. You have to flip this graph over on its 90 degrees here to get a relationship here. Okay, so what we've done here, I've got it shown in green, that feasible region or that profit region that we graphed out here. We got those different corner points here. And the key that we want to take away from this here is this here. We determine our maximum profit here at 75S 90B at this point, at this corner point here. That was our deal. And what it is this is how you want to use this. If you have no other means of looking at this here, and you want to understand your different profit levels and understand where you're going to get your maximum profit, we take, this is called a gradient vector line here. We started at our 0, 0 coordinate for S and B here, and we moved up to that 75, 90 coordinate here for S and B here. So that was our maximum profit line here based on that profit function that we're maximizing here. And this graph is actually laid out in using some optimization program here, and I've done it in MapleSoft. But you could a computer software package here for optimizing linear algebra functions or linear programming here. But you could lay this out here by hand if you knew nothing else here. So you have determine your gradient vector line here based on that maximum profit point here, and then you're going to have what they call these level curves or equal profit curves here, and actually they're just linear function here. So you're going to have this gradient vector line is important here because if you take any point on that vector line and draw a line 90 degrees to it, any point on that 90-degree line, just take this in here, is really apportioning your B and your S different products here. So you're going to get, using that 90-degree perpendicular line here, you can determine the profit here. It's going to be the same depending on your combination for S and B here on that line, regardless where it is here. We determined our point here, but you can take it if you have anything less, if you're building less units here in some combination that you're looking at, you can just take a proportionate out here. So if you got a point, say on this level curve at this point here, so you just go down to B here, you determine how many B units that is here, and then you just project that over to our S units, and you can determine how many S units you have for the equal profit. So really these are the level curves here, they're equal profit lines, and they're 90 degrees to the gradient vector line. So this is a key thing here. The green area is what we call that feasible region or the profit region based on our graphing here, and the constraints create this region on this plane here. Okay, so that's our constraints, and that's our profit function here, what we want to optimize. Constraints are set up by these lines that we have graphed out here in our feasible region. We can have any profit in this region here because remember we talked about less than and greater than here for those different deals. It has to be greater than 0 here, less than a certain, depending on the lines here. Okay, so that's basically what we're talking about with determining a different profits. Just remember the gradient vector line here is a straight line from 0 up to where you have your maximum profit. That's going to be your steepest line here, and any point, any line that you establish perpendicular or 90 degrees to your gradient vector line, you can follow that line here to determine the different profits or different combination of, in this case, these S and B products here to determine the profit. Okay, so that takes care of our looking at our constraints here, looking at it in this, setting up a plane here to determine our profit areas here for those two different products based on the constraints. And then let's go down here. Okay, so going down here, let's just look at it in terms of 3D here. We always look at numbers here. We looked at it in terms of 2D here, but let's just look at those functions here in terms of a 3D plot here, just to understand what's going on here. So what we've got here, remember that those bounded lines here, I'm showing that down over here, all of that blue line here and that green line here for our material constraint here in B, and then this red line here. Okay, so what you do, this is our 2D area in here. So we got our product S increasing along here, and then our product B here increasing along this axis. So what we've essentially done here, and this is what the computer would be doing here, and what you'd be doing here by hand, you're going to come up with some maximum profit. Remember, we came up with that maximum profit here being $51,750, and that's really just a projection, a 90-degree projection right above that maximum profit coordinate here, 75 here for S, 90 here for B, based on our two-dimensional graph. So we just project that line up here. And then we have this, and that's our just our profit line that we're looking at here in 3D. And then based on that profit function we're having, we come up with a profit. It's really a profit plane here that based on that, in this case, you can just look at it, that 240S plus 375B. So looking at it in terms of 3D here, that's our profit line up here. So that plane that's a 3D plane, or a three-dimensional plane here, X, Y coordinates along with our profit function. So it gives you a little idea what's going on here. So this 90-degree line here where we come up with our maximum profit at that point is projected right up here at 90 degrees. It's where it intersects that plane, this profit plane here, that is where you get your maximum profit here. So you're dealing with that gradient line coming off of 0 here, and that's where you're going to, it's sitting really on this profit plane here, and that's where you get your steepest slope here. So just to understand it, gives a little perspective of what you're talking about here when you're maximizing or doing linear optimization here. And this is really what we looked at, the 2D plots here, but putting it in 3D, we added in that maximum profit, or our profit function here, based on those 2D or feasible range or the constraints that we established. So just remember that. Just plotting it up here based on that where we get maximum profit, plotting it up here where it intersects our plane, that gives our maximum profit, just to give it a little understanding. And then one last thing here. I've done the same thing here in 3Ds. If we looked at and plotted, we just plot out these red lines. Those are those perpendicular lines here to our gradient line, that profit function here shown in blue here. Those are those level curves or equal profit curves, and those can be related back to our different. These are these things here. These 90-degree curves here to our gradient line here, our gradient vector line here. That's all I'm showing here. We got our profit going up here. Product S increasing this way. In this case, product B increasing this way. But these, just to understand, it gives you a little, it's a 3D profit graph here. We're looking at 3Ds in both of these cases here. So it gives you a little different understanding here. When we looked at it in just that 2D plot here, those were the lines here, and you can see those gradient lines here. They're increasing. We started out 0, 0 here, and we moved up here. I'm not showing the different below here. I'm not showing our line intersects where it bounds. I'm just showing, get a good understanding here of what we were talking about. We looked at it in 2D up above here for that feasible region, and we looked at our level curves here, just making that relationship. Okay, so we went through just a basic example here where we used maximizing some, using some linear algebra or linear program here to maximize some profit here on two different products that we're selling, and basing it on the contribution margin along with the capacity constraints we have in these products. We're able to determine the maximum profit that we could, that point here where we would have some maximum profit. Okay, so this is just a basic example, give you a bit of understanding of what's going on when you're dealing with linear programming here and getting and how you would handle it. Okay, maybe there's one last thing we want to talk about here, going down here. Now, we wouldn't have to go through all this here. It's really just a simple matter of taking some, and I'm using MapleSoft Computer solution here, and just under their optimization package, you just put in, they have a function here called LP solve, and there would be different, you could do this in Excel as well here, so Excel has some optimization package here, but LP solve, in this case I put in my objective function here, 240S plus 375 times B here, and then I got the different constraints that we have here, B greater than 0, S greater equal to 0, and then B less than 110 here, and then there's two other constraints here, the different line constraints here for the assembly and test time. Set some range in here, hit the set it at maximize, and you come up with the maximum profit here, 51,750, and this is, I get B is equal to 90, S equals to 75 here, in this case here. Okay, B equals 90, yes. S equals 75. Went back and looked at my 2D graph to make sure it was the same here. But just to give you the power here of how you can come up with some constraints here, just looking at it in this case, it would just take some software package. You can, many of the calculators have that built into them here. Just put in, determine your what you're going to optimize here. In this case, it was based on an objective function where we're looking at contribution margin. Set in some constraints here, and then hit enter, and you're going to come up with the solution here that we looked at. So this is very easy to do here, and it'll only probably take you a minute or so, and you come up with the solution. But we went through it by hand here to determine exactly what we'd have to do to determine those different, maximize our profit in this case.